Okay, so let's say that we're talking about tantalinium. Okay, and we have, what is the chemical formula for tantalinium?
Chemical formula, you guys?
Let me spell it for you. Oops. Tantalinium. So what is the formula?
Ta.
Or the chemical symbol, Ta. Okay, so we have Ta. Can you guys see the green? Or should I use a different color? Green's good?
Yeah.
That works.
Okay, and then we're talking about, let's say, Ta 6 plus. Okay, so what would be the electron configuration for Ta? I heard 1s, 1s2. Okay. What's next?
Atomic number 73.
So somebody said it's atomic number 73, right here. So we got 1s2, 2s2, 2p6, okay, so we're up here, so we've done that. And then somebody said 3s. 3s what?
3s2.
3s2. Okay. And then
3d10, right?
3p what?
Oh, 3d10? Is it that?
Would it be 3p10?
D10.
What?
What is it then?
Well, okay. So if we were doing it in accordance of the periodic table, it would be 3p6. Okay, so then that would be that. And then it would be 4s2. Now it's 3d10. Then 4p6. 5s2. Four D10. I'm running out of room. Let me see if I can shift this over a little bit. Oops. Hold on a second. So we said, so 4s2, 4d10. Okay, what's after 40 and 10? So then that. Five P6. Okay, after 5p6, 6s2, okay, so here you said I heard somebody say 5d6. Wait, would it be 5d6?
Or F14.
Or F14? Okay, we got 4F14, and then we have this guy. That's 1, that's 2, that's 3, that's 4. So then that would be 5d4. Okay, everybody see that? Okay, is there a shorter way of writing this?
Start at XE.
Okay, start at XE. So let me make space for it. Because that was a lot of work. I don't know about you guys. Did you guys enjoy doing all that work? I heard a question, but I couldn't hear what they actually asked. I heard the question, but what was the question? So another way of saying it, you said start off with XE. And I'm going to put that as in brackets. Okay, and then
6S2.
6s2. And then
Or F14.
for F14. And then
5D4.
okay, so now that's a lot easier, right? Nice and clean, easy to see. Okay, so if we're talking about TA 6 plus, what does that 6 plus mean? Taking away electrons. That is correct. Okay, so if I was taking away electrons, I'm taking away 6 of them. So where am I going to take them away from? Let's use the short nomenclature. So we're going to start with that XE. So if I was taking away 6, where am I taking them away from? Okay, so I'm going to be taking them away from 6S and the 5D. So then I'll just have 4 F14 left. Because we know that we're always going to take away from the outer shells, which is the higher numbers. Okay? Simple?
No, can you like break this down? Because I don't even understand.
Okay, yes. Okay, so first off, electron configuration is trying to keep account of all of the different electrons that are in an element. So TA has a total of 73 electrons. Let me erase that so you guys can actually see because we know that the number of electrons always equal the number of protons for an element. Okay, so if we're keeping track of all of the electrons. We're saying where they're located at, which orbital they're in, and which period, right? And how many are there. And so if you take a look at this corner, you see where I say 1s, 1s2. So we're going to TA. This is what we're trying to get to. We're going completely from the beginning. 1s2 represents you have an electron that would be here and here. So that these two represent the 1s. The s orbital can only hold 2 electrons. So that's the most that the s can hold. So then after we get to the 1s, this is the second period. That tells me the number that goes right in front of it. And then it's the 2s. So then we fill up the 2s. And that can hold 2 electrons. That represents those 2 electrons. Okay. Then it goes to the 2p, right? So this here represents the 2p spot. So that occupies, that's where the electrons can go for that 2p. So there's a total of 6 spots that could go into. So that's the 2p6. And then we go to the third period. And then we start again with the s. The s, then over here, it's the p. So 3s2, 3p6. Are you getting a trend, Aria? Ara?
Yes, I get the as far as the I'm trying to say, I don't even know how to explain it. But as far as the shells, yeah, as far as the shells go, I get that part. But I'm trying to understand like the XE6, like when you made it shorter.
Oh, the shorter part of it. Okay.
Yeah, like I don't get that part.
Okay, so here is TA, right? So if we go to the noble gas represents stability, right? So that XE says that you have all the same electrons as that noble gas does. That's what that means. So all of the electrons before that are taken into account by using the XE. So I can just use the XE. So I'm going to underline what it represents in blue. So you see that top line? That top line is the full electron configuration. And so from the 1s all the way up to the 5p6, all of that is represented by that XE, right? So it's all, it's all of this right here. So you always go to the nearest noble gas before the element that we're looking at. So we're looking at TA, the nearest noble gas before the element TA is XE. So we're going to use that. And so all you're saying is that we have all the electrons that XE has in brackets. That's all you're saying. That's all of those electrons. That is called your core, right? And that core basically means those electrons you don't want to mess with. They're like in saving. You don't want to mess with them at all. They're not going to be involved in bonding at all. Where these electrons right here, actually different color. In pink, right here, those electrons, those can be involved in bonding. Those are called your valence electrons. Okay, so these electrons that are underlined here in the blue, those are kind of like hidden in a vault that you can't get to and touch at all. The only ones that you can use is the ones that are here in pink. Okay, so those are the ones. So these guys are called valence electrons. And then these guys would be your core electrons. So rather than writing all of these out, because it's always going to be the same, you can just use XE as that marker, because here that basically means that it's completely full because it's a noble gas. They have a completely full shell. So you'd use that XC. That would be completely full. So if we got rid of all of these electrons, it would be just like XC, and it would be completely full. It would be stable if we had gotten rid of all of those. Okay? Does that make sense?
Yes, that makes a lot more sense now. I feel like I understand.
Okay, good. Okay, now when we're removing electrons, we always want to remove from the highest period or the highest level, right? So 6 is greater than 4. So we're going to remove from 6 first. Then we're going to remove from 5. And then if we need to remove, we'll remove from 4. Does that make sense?
Yes.
Okay. Okay, good. Good. Anyone else? Any other questions on this? But those are good questions. Okay. So let's move a little bit forward. Okay. So if we're writing the electron configuration for cobalt, what would it be? The short way. Are you guys there?
Yes.
Argon in brackets.
Argon in brackets. Okay.
Or S2.
Okay.
3D7.
Okay. Piece of cake. Okay. Okay, let's see. Okay, so now when we talk about valence electrons, a large time when we're talking about these chemical reactions that we're going to be looking at, we're going to be looking at certain elements more in the main group than the other groups. And when we're talking about the main groups on the terms of the periodic table, we're basically not going to be taking into account the, well, we're not really going to be taking into account the D or the F subshells. So we're looking at just the S and the P, right? So if we take a look at the S and the P, let's say we look at period 2, count across on period 2, how many boxes are in period 2? How many boxes are there in period 2? 8. Right? So if we take a look at it, we know that the S part, this here represents the S. We know that that can only hold 2 electrons. And we know the P part can hold how many? So the P can hold 6. Okay. Okay, so the S holds 2, the P holds 6. Altogether, that adds up to 8. So there's 2 plus 6 is going to equal 8. Now, if you look at it, the noble gases, excuse me. Okay, the noble gases basically will have what we call its octet full. So their outer shell is completely full. for the noble gases. That is what allows them to be stable. It's the fact that they are at a completely stable state where they have all the electrons that they need to have a full shell. Now, if we look at it, regardless of where we go, if our S and our P outer shells, if those are completely full, those are going to be your outer shells, right? Because here we have 4S. This guy is 3D. And then this one is 6S. This guy is 4F. So if we got the S and the P completely full, then the outer shell is completely full, because we've already incorporated these in other earlier energy levels, okay? So when we look at this, we have a total of 8 electrons to sit there and have that octet full. So when we talk about our valence electrons, we're looking at the electrons primarily that are going to be occurring with these guys and these guys. Again, the transitional metals and the actinoids and the lanthanoids, those guys are going to behave a little bit different than normal, but these guys are always going to behave the same way all the time. These guys in group 1, they always are going to have what we call 1 valence electron. So if we write down the electron configuration in terms of like a core and valence electrons, so like lithium, it's going to be, what would be the core for lithium? What would be the noble gas that we would use if we write down the electron configuration for lithium?
Helium?
Helium. So we'd use He, right? And then we would say lithium is, it'd be 2s, 1, right? Are you guys with me? So the number of valence electrons that lithium would have would be what? If this is the core, that means we're not touching it at all. How many electrons are in that 2s orbit or shell?
1.
1. There's 1 electron. Now francium, if you're writing the chemical formula, the electron configuration for francium, what is its noble gas? Rn. And then we would write what afterwards? 7s, 7s1. How many valence electrons do we have there? 1. Okay, so regardless of what element it is in group 1, they're always going to have 1 valence electron. So I can write group 1 as being NS1, right? N representing any number, and S, so it could be any period, right? So it's 6, it's going to be 1. Then I'm always talking about group 1. So anything in group 1 is going to have this generic notation because it always has that core, and then it has just that 1 electron. You guys understand that? Okay, so let's see. If I do the electron configuration for manganese, and then we'll do it for barium. So manganese, so what would be the electron configuration for manganese? The easy way. Its noble gas is what? Neon. And then? Okay, now what about barium? Ba. Its noble gas is Xe. Okay, and then I can't hear you guys.
S2.
S2. Thank you. Okay, so anything that's in group 2, it's going to be written as NS2. Okay, so basically it could be any period, and then it could have an S2. Do you guys kind of see the pattern?
Yeah.
Okay, so now what about group 15? This is group 15. What would be the pattern for that?
Is it gonna be 3?
What was that?
Is it gonna be 3?
No, because we know that how many electrons can we hold in the s orbital?
How many? 2.
We can hold 2. So that represents here. So that's 1. And let's do this one. 1, 2. Okay. So we know that it's going to have to at least have NS2. And so who's in group 15? Nitrogen? Okay. So that's 1, 2 for that NS2. And then N meaning any number. So then that's 1, 2, 3 for nitrogen. So then that would be NP3. So anything in group 15 is always going to have a number S2, a number P2. Okay, so let me give you an example. Let's do nitrogen. So what would be the electron configuration for nitrogen using the noble gas shortcut? So we'd use, what would be the nearest noble gas? Before the nearest noble gas before the element?
Avanos is helium.
Helium. Okay. Are they getting tired of yelling at me? So
Little.
helium. And then
2s2.
2s2.
2p3.
2p3. Okay. Now what about anthony? SB.
Guys, quiet down, please.
In brackets.
Brackets. Okay.
Krypton.
Okay. KR. Okay.
5s2.
Okay.
4d10.
You said 5p3.
You guys are gonna talk whisper.
Is it 4d10?
Ah, okay. So here in this case, where are we? Anthony. So you said 4d10. Oops. Okay, 4D10, and then
5P3.
5p3. Okay, how many electrons do I have in that outer shell? As in the outer period.
5.
So I have 5, right? So I have that 2 that are in the S, and I have 3 that are in the P. So I have 5s2, 5p. So this guy is a lower level. So we're just looking at these guys, because these guys are going to be the ones that are going to be easily available. This guy's available. These guys are going to be easily available because they're in the outer shell, right? So they still match up with that NS2 NP because that N represents that outer shell. Does that make sense?
Yeah.
Okay. So when we're talking about valence electrons or electrons that are going to be readily available for reacting, you're going to have those 5 electrons because it's in group 15. So these guys are always going to have 5 electrons because readily available for reacting with. That also means that there's only 3 electrons that it needs to get to sit there and be like a noble gas. So it needs to somehow get a hold of 3 more electrons to be like a noble gas, okay? And so all of these guys in that group are going to behave pretty similarly in terms of reactions, except when we get down here for other reasons, okay? Are you guys with me so far?
Yes.
Okay, so typically when we're talking about main group reactions, so we're going to be looking at just the S and the P because those are going to be the ones that are going to be readily available. And then we'll start looking to the D if we need to. Okay? And that's basically what this slide is saying in so many words, is that we're just going to be looking at the P, the S, and the P. The 2 electrons in the S and the ones that are in the P, right? Okay, so this is another way of looking at it. So anything that's in group 1, this is that NS1. Anything in group 2, those guys are always going to be NS2. In group 3 of that main group, so that's where aluminum is at. So that's going to be NS2, NP1, and so on and so forth as we go across the periodic table, right? So this is the main groups. So this one, group 1, group 2, and then basically 13, 14, 15, 16, 17, 18. Those are going to be your main groups. Okay. Now, when we talk about those guys having valence electrons, another way of doing valence electrons is by using a dot. If it has 1 valence electron, we use a single dot. So like sodium has 1 valence electron. So we use a single dot to represent that electron that we can use for that reaction. Magnesium has 2 valence electrons. So that means that we can use those 2 electrons for reactions. Aluminum has 3 electrons. Silicone has 4 valence electrons. So that means there's 4 that we could use for that reaction. Phosphorus has 5 valence electrons. So 5 electrons for reactions. You guys see that? You understand it? So we go to the periodic table. If we're looking at just the main groups, so that's, as I said, 1. That's 1, 2, 13, 14, 15, 16, 17, 18. So all those in group 1, they're always going to have just a dot. That's going to be representing the electron that they can use. Those in group 2, those guys are going to have 2 dots. Those in group 3, these guys are going to have 3 dots. Those, that main group 3 or group 13, 3 dots. Those in group 14 are going to have 4 dots. Those who in group 15 are going to have 5 dots. and those in group 16, 6 dots, those in group 17, 7 dots. So basically meaning they have 7 electrons that could be used for reactions, right? So the way that we would draw that out in the Lewis dot structure is that we would put, like in the case of fluorine, 1, 2, 3, 4, 5, 6, 7 dots around fluorine. So that would be the Lewis dot structure for fluorine. Are you with me? Okay. Now, if we looked at, let's say, neon, how many dots are going to be around neon? I heard somebody say 6.
Yeah, 6.
So there's 1, there's 2, there's 3,
3,
there's 4, there's 5, there's 6, there's 7, there's 8. So there's actually 8 because we have the 2 that are in the S and the 6 that are in the P. Okay, so all noble gases have their outer shell full. So in other words, they have 8 dots surrounding them. So that means that they've reached what we call an octet, meaning 8 around them, except for helium. Helium only likes to have 2 around it. And that's it. So it's only going to have 2 dots. And then it's happy. Where all of the other noble gases are going to need to have 8 dots around it. You're always going to be looking at your S and your P. Okay? So we're going to be looking here, S and our P, when we look at radon. So it's going to have 8 around it. Okay? Okay, so let's see if we can answer some of these questions. Clear. Okay, write the electron configuration for the highest occupied energy level for group 6A/16. So group 16 elements. So in other words, write it in a generic form, kind of like what you see down here in this form. So how would we write group 16 elements in this form? Okay, so let's look at group 16. Oops. So group 16, we have, where's group 16? Which elements are in group 16?
Oxygen.
So we have oxygen. Okay, so it's this group right here. Okay, so if I want to write it as NS, NP, what are going to be the exponents? NS what? Oh, we're not talking about specifically for we're talking generically for all of them.
NS2.
NS2, okay, and NP what? How far is it over in the P? 4. Right, so it's NS2, so it's 2, and then 1, 2, 3, 4 for the P. You guys get that? Okay. Okay, second part of the question, it says to identify the group whose electron configuration is the highest occupied level, NS2 and P2. So which group would be NS2 and P2.
Group 14.
Right, group 14. Okay, because here's your 2s, your 2 s's, so this would be 1, 2, and then 1, 2. Okay. So we talked about how the Lewis dot signifies the number of valence electrons. Now, we're also going to be using the Lewis dot structures or the Lewis dot symbol to sit there and signify bonding. Because we know that everybody wants to be like the noble gases, we want to try to get it so that the octet of all of the elements are completely full. So for instance, if we have oxygen, and we want to draw the Lewis symbol for oxygen, what is the Lewis dot structure for oxygen? Just oxygen alone. How many valence electrons? We have 6 valence electrons, so that's 6 dots around it. Okay, now if I have oxygen and oxygen reacting with each other, which it does to form oxygen gas, so each of them will have 6 valence electrons that they can use for bonding. And they're going to form, what type of bond is 2 non-metals going to form? You guys remember this from last week? 2 non-metals form what type of bond? Is it going to be an ionic bond? Is it going to be a covalent bond? Is it going to be a metallic bond?
Covalent.
It's going to form a covalent bond. Okay, now when it forms a covalent bond, it is going to want to try to get 8 electrons around all of the atoms in the compound. So it's going to share the electrons so that each one will have 8 around it, except for hydrogen, which will only want to have 2 around it because it wants to be like helium. Okay, so if I'm doing O and O together, I'm going to adjust those dots so that I have 8 around, 8 dots around both elements. Okay, so that's 2, that's 4, that's 6, that's 8. So that oxygen has 8 around it. So that's 2, that's 4, that's 6, that's 8. That oxygen has 2 around it. Now, these dots that are being shared, these are shared, so those are bonded electrons. The way that we show bonded electrons in the Lewis dot structure is by a line. 2 dots represent a single line. So that would be a shared bond. So this would be the Lewis dot structure for oxygen gas. So that's 2, 4, 6, 8 around that oxygen, 2, 4, 6, 8 around this oxygen. And them having 8 around it, they're going to be like a noble gas with their outer shell completely full. And so they're going to be more stable. Does that make sense? Okay, good. Okay, so let's say I have nitrogen and nitrogen. Okay, how many valence electrons does each of the nitrogens have?
5.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if nitrogen and nitrogen are going to form nitrogen gas, so how can I make this structure so that we have 8 electrons around each one of them? How many electrons have to be shared?
3.
You said 3? So each one has to share 3? So then that means there'll be 2 left over here, 2 left over here. So in other words, we're going to have what we call the triple bond. 2, 3. Okay, so let's make sure that we have 8 around them. That's 2, that's 4, that's 6, that's 8 around that nitrogen. There's 2, 4, 6, 8 around this nitrogen. So everybody's octet is full. It's happy. So it's good. Okay, so again, this is a triple bond because we're sharing 3 pairs of electrons. This guy is sharing 2 pairs of electrons, so that's a double bond. So what about a fluorine? How many valence electrons does fluorine have?
7.
It has 7. So how many electrons have to be shared for it to reach its octet of having 8 around it?
Four.
Somebody said 4?
Yes.
1.
You're saying, okay, so I'm going to draw out what you just told me. So I'm going to have 4 in the middle. And then I'm going to have 3 on the outside. Because that would be. Okay, so then if I count the number of electrons around this fluorine, how many do I have? How many? Count, how many is there?
11.
There's 7? Remember, you're counting the ones that are being shared too. They're being counted as well.
11.
Oh, you said 11.
Yes.
11. So is that 8?
No.
No. So does that meet the octet rule?
No.
Okay. So 8 meaning, octet meaning 8. So we know that this does not work. Okay. What else do you guys suggest?
1.
You said 1? Okay. So let's try that one. So we have, you said 1, 1, and then. So if each of them share 1, okay, so then that's 2, that's 4, that's 6, that's 8. So that's 8 around this guy. So we have 8 around this guy here. And then we have 8 around this guy here. So that obeys the octet rule. So then we can go ahead and write it the way we want. With our line right there and having 6 around it. Okay, are you guys with me so far? Avenel? Yes, I heard no. No? Okay, so let's try it differently. Let's go to the periodic table. So let's break this habit. Let's do CO, carbon monoxide. Okay, how many valence electrons does carbon have? Where's carbon? What is the atomic number for carbon? I heard 6. So carbon has the atomic number 6, okay? So how many valence electrons does carbon have? The easiest way is to
5? Oh,
count across to carbon, starting at the second period because that's where it's at. So
right.
you're only
1,
going to
2,
count
3,
the S
oh,
and the P.
4.
4. So we know that carbon is going to have 4 dots. 1,
Mhm.
2, 3, 4. So carbon has 4 dots. Okay. Oxygen has how many dots?
Oxygen has 6.
Oxygen has 6. 1, 2, 3, 4, 5, 6. Now the electrons are movable, right? So our goal is getting it. So by sharing electrons, we want to try to get 8 electrons around each of the elements. So I want to get 8 around carbon, and I want to get 8 around oxygen by moving the electrons, and the ones that are between the two are being shared. Okay. So how do I want to move these electrons? First, I'm going to move it to a place where we don't have a big old blue dot at the very bottom. How about that? Okay. How many electrons am I going to move towards the middle? So that each element has 8 around it, carbon and the oxygen. And I could take more from one than the other if I need to. Am I going to move this one? Are you guys there? So if I move those 2 in the middle, right? And we'll assume that they're going to be sharing those 2. How many is around carbon?
2, right?
Count on both sides around it, even the stuff that's in between right now. So there will be 2 here, and there will be 2 here around carbon. Is that 8?
No.
Okay, so we know 2 plus 2 is not equal 8, right? So we know that it's not going to be a single bond. So it's not just going to be sharing 2 electrons. So I need to add more. So if I take these 2 and I add those to the middle, organize this a little bit better. Sorry, it's a hot mess there.
Wouldn't carbon have to give away 2? So it'll be 4 shared between them. So
Okay,
then
so
oxygen has 8 and then carbon just have 2, right?
so you're saying, so, okay, so let me see. So you're saying I have 4 between them, right? Like I have right now, right? That's
Yeah.
4 between them. Okay, so then that's 2, that's 4, that's 6 around carbon. Is that 8?
No, but carbon has to give 2 to oxygen.
And well, it's sharing 2. So you're saying they need to give another 2?
I don't know. Yes.
Okay, so we'll go ahead and do that, right? So if we take those 2 and we'll move those over. So how many electrons do we have around carbon now? Just count those
Just
in the
2.
middle. No, count the ones that are around carbon. So like what I'm saying is, I'm going to draw a circle around it. Give me a second. A green circle. Can you guys see between, anybody colorblind? Blue-green colorblind. How many electrons are around there? The dots. How many dots do you see? Around carbon.
6.
6. Is that 8?
No.
No. Okay, so we know that that does not work because we need to have it so that there's 8 around carbon. So let's go ahead and move. We're going to move some of them around here. Okay, but what if we get another set from oxygen? And we move that to the middle. Okay, how many do we have around carbon now?
8.
We have 8. Right? So that's 2, that's 4, that's 6, that's 8. Okay, how many do we have around oxygen?
8.
So we also have 8. So if we look at the purple, or the pink, whatever you want to call it, 2, 4, 6, 8. So that would obey the octet rule. Both have to have 8 around them. So we could draw this structure like this. Each line represents 2 electrons being shared. With 2 valence electrons around them or surrounding. So these guys here, these here are called lone pair electrons. Those guys are ones that are not involved in bonding. Okay. So do you guys understand the octet rule? Does that help a little bit? No? I hear yes, and I hear a no. Okay, let's try one more time. So we'll try a different one. Let's try water. H2O. So now you have 3 atoms. One of those atoms are going to have to be in the middle. So the thing that we know, or what we should always know, is that hydrogen only needs 1 more electron to be like helium. So it's only going to want to share 1 electron with someone so that it can be like helium. It can't have more than 1. So it will never, ever be in the middle. So who's going to be in the middle if hydrogen can never be in the middle?
Oxygen.
Oxygen, yeah.
Okay, so oxygen is going to be in the middle. Okay, how many valence electrons does oxygen have?
6.
It has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. How many valence electrons does hydrogen have? 1. Okay, so can you guys rearrange these dots so that everybody has either, in the case of hydrogen, has 2 around it, and the case of oxygen has 8 around it?
Each hydrogen has to share their electron.
Each hydrogen has to share an electron, okay? So you're saying this way, and then that will leave us with 1, 2, 3, and then like this. Okay, so let's check to make sure we're right. So that's 2, that's 4, that's 6, that's 8 around this hydrogen. That's 2 around each, that's 2, 4, 6, 8 around this oxygen. That's 2 around hydrogen and 2 around this hydrogen. So that obeys its rule. And we had a total of 1, 2, 3, 4, 5, 6, 7, 8. 8 total electrons, 2, 4, 6, 8. So everything checks out. Simple? Yes, no, maybe?
Nah, can you explain it again? Because now I'm kind of like, I'm a little lost now.
Okay. So again, we want to make sure that everybody is octet. So we're saying that this hydrogen is going to share. I'm going to put this in a different color. it's going to share one electron, right? It's going to take one of the electrons here with this hydrogen, with the oxygen. It's going to share that. It's going to take this here and it's going to share that, right? So those are the ones that are being shared. So these electrons, we're just going to move those down here to make it cleaner. I'm going to put that in a different color as well. So these electrons, I'm just going to put down here to make it a little bit easier to see. Okay, so I move these two electrons here. This here represents the two electrons that are represented by the line, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around oxygen. So its octet is reached. We have 1, 2 around this hydrogen. So its octet is reached. We have 1, 2 around this hydrogen. So its octet is reached. Right? So again, you want to get it so that you have 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. The line represents 2 electrons that are being shared for each line that you have. There's 2 here, and then there's 2 what we call lone pairs. Does that make better sense?
Yeah, it makes sense. I forgot earlier when you said that electrons are movable. So when hydrogen shared, so then the 2 that was by themselves paired up,
Yeah.
which gave oxygen 8. So
That's right.
okay, I got it. Yeah.
Yeah. And so you got to remember, so the electrons are always going to be movable. So they can be moved from element to element if they're being shared. Okay. So let's see if we can make it a little more challenging. Okay, so there's the way that you determine who's going to be in the middle. There's going to be a couple of ways to determine. One of them is called what we call the electronegativity. If you guys look on your P table, you go here, you click down to electronegativity. This here is the scale of electronegativity, right? So it goes from the lowest value that you'll see here is 0.7, right? So 0.7, that's going to be our lowest value, and our highest value is 3.98 or 4, right? So lowest, highest. Electronegativity is the desire to want to pull electrons towards you, right? So you're pulling it towards yourself. So when you're sharing it so that it favors you and not the other partner. The higher your electronegativity is, the more you're pulling it towards yourself. The weaker your electronegativity is, the less you're pulling it towards yourself. Okay? So if we look on the periodic table, there's a general trend. As we go from left to right, the electronegativity increases in this direction. As we go from top to bottom, the electronegativity, as we go from left to right, the electronegativity increases. As we go from top to bottom, the electronegativity decreases. So you get weaker electronegativity as we go down. So for instance, oxygen is stronger than sulfur. So oxygen is 3.44 in terms of electronegativity. Sulfur is 2.58. Okay, do you guys see that? Yes, no, maybe? Okay, yes or no? Do you guys not see that?
Yes.
Okay, good. So the rule is, okay, how many of you guys have siblings? How many of you guys have brothers and sisters? Okay, siblings are brothers and sisters. Okay, so now, how many of you guys have at least 2 brothers and sisters? Okay, so for those who have at least 2 or maybe more, so how do you guys decide who sits in the middle in the back seat? What was that?
The youngest.
The youngest? Okay. So And why is it the youngest has to sit in the middle?
You got to be protected.
Okay, so they have to be protected. Okay, so as a sibling, do you look at it as you have to protect them, or is it because they're weaker than you are?
Yeah, that too.
Yeah, that too. So in other words, you're saying the weak one gets put in the middle. Is that what you're telling me?
Yes.
Okay, so this should be really easy for you to understand. So the way we decide who goes in the middle is the weak one, whoever has the least amount of electronegativity. So in this case, we have hydrogen, we have carbon, and we have nitrogen. Now we know that hydrogen can never, ever, ever be in the middle. So we'll never put him in the middle, right? So that hydrogen is kind of like that special sibling that always throws up on road trips because they can't be in the middle, right? So they always have to be next to the window so they can vomit out the window, okay? So that's what hydrogen is. You're never gonna ever put hydrogen in the middle. So then you're gonna put the one who's weakest. Who's weakest between carbon and nitrogen? So carbon is weakest. So carbon is gonna be in the middle. So how many valence electrons does carbon have? How many?
4.
4. So that's 1, that's 2, that's 3, and that's 4. What about nitrogen?
5.
Nitrogen has 5. That's 1, 2, 3, 4, 5. And hydrogen?
1.
1. Okay, so now what I want you guys to do is to look at this on your piece of paper. Find a way so that everybody's octet is full. Hydrogen has 2 around it, carbon has 8 around it, and nitrogen has 8 around it. Okay? And then I want you to how many of you guys have Chromebooks? All of you guys? Horrible, horrible. Okay, so you guys got it?
Yes.
Okay, so who's gonna be in the middle?
Carbon.
So we're gonna put carbon in the middle. Okay, how many bonds between carbon and nitrogen?
3.
How many lone pairs on nitrogen? Lone pairs are the dots that'll be left over that are not involved in bonding.
1.
You said 1 dot, or 1 lone pair? Like that?
No, only 1.
Only 1 dot?
Yes.
Okay, I'm gonna do what you tell me to do.
I think
Okay,
you had it right the first time.
what was that?
I think you had it right the first time.
You think I had it right the first time? Okay. Okay, am I done?
And then 1 bond with hydrogen.
1 bond with hydrogen. Any lone pair on carbon?
No.
Okay, so let's do a count. So let's count how many are around hydrogen. How many electrons do we have around hydrogen?
2.
2, because the line represents 2, right? Okay. And then how many do we have around carbon? 8, that's right. And then how many do we have around nitrogen? 8. So did we obey the octet rule?
Yes.
Yes. Okay. Okay, so that's Lewis dot structure. Okay, and we'll go over more of those, promise you. Okay, so now let's talk about some general trends on the periodic table. So as we look on the periodic table, as we go from left to right, the size of an atom is going to decrease, right? As we go from top to bottom, the size of the atom is going to increase. Now, let me show you this. So as we go from left to right, it gets smaller. As we go from top to bottom, it gets bigger. Okay, you guys see that, right?
Yeah.
Okay, so there we go. Okay, so the reason why it gets smaller as we go from left to right is because at the center of the atom, we have protons and their neutrons. So those guys are going to be pulling the electrons in because the atom consists of protons and neutrons in the center and electrons orbiting around it. So the electrons are negatively charged. They're being pulled in by the number of protons that you have. The more protons that you have in the middle, the closer it pulls the electrons towards it. Okay, so if we compare one proton to two protons is more. So it's going to be pulling more than that one proton is. Okay, and that's the same thing as we go across here. Okay, in terms of size. So size-wise, the atom is going to decrease in this direction, right? And it's also going to decrease as we go up. Now, the reason why we get an increase as we go down, right? Francium is much bigger than hydrogen. Well, remember we talked about the Bohr atom and we said that the electrons are orbiting and they have different energy levels. And those energy levels, have you guys seen Russian dolls? The little dolls that it's a small doll and you put a bigger doll around it and you put a bigger doll around it and you put a bigger doll around it and you put it so on and so forth. Have you guys seen that before?
Yeah.
Okay, so these periods, right, on the side here, get over there. These periods, these guys, they are kind of like those Russian dolls. So this is the first one is that small doll. This one is the bigger doll. This one is the bigger doll. This is the biggest, you know, so on and so forth, right? So francium is going to be the really big doll, where hydrogen is going to be that very little one that we put in the very center. Okay, so does that make sense? Yeah, no, maybe.
Does that make sense, everyone?
Yeah.
Okay, so this basically just shows you that increase. Okay, so refer to the atomic table or the periodic table and list the atomic numbers 15, 16, and 33 in order of increasing atomic size. So which one is going to be the biggest to which one, which one is going to be the smallest to which one is going to be the biggest? What's going to be the order? So if we go to our periodic table, we're looking at the atomic numbers of 15, 16, and 33. So what are the atoms that we're looking at?
Phosphorus, sulfur, and arsenic.
Okay, so we're looking at these guys right here. Okay, which one is going to be the smallest?
Phosphorus.
Okay, you say phosphorus is going to be the smallest. Are you sure?
Is it AS?
AS is going to be the smallest? I heard somebody say sulfur. So why is sulfur going to be the smallest? Which way does size increase?
That's right.
Is it from left to right or from right to left? Increase. So we're saying that sulfur is smaller than, who's going to be next if it's sulfur?
Phosphorus.
Phosphorus. So Pac-Man eats the bigger one. So Pac-Man. Pac-Man eats the bigger one. You guys remember that? Maybe not. You guys don't even know what Pac-Man is. I'm wasting my time. Okay, so why is sulfur the smallest again? Who has more protons? Phosphorus or sulfur? Which one has more protons? Phosphorus or sulfur? Phosphorus? Did somebody say phosphorus or did somebody say sulfur? Oh, sulfur. I could hardly hear you. Sulfur. So we know that sulfur has more protons, right? And remember, protons are going to be pulling these electrons closer to it, right? The more protons you have, the smaller you're going to get. You're pulling everything closer to your body, right? So you're smaller, you're tight and more fit, okay? Where phosphorus has less protons, so it's going to be less fit. It's going to be a little bit bigger, okay? And then we know that arsenic is going to be bigger because you're adding a whole nother layer. You have a whole nother layer of fat added on there, okay? Okay, so if we look at the periodic table, who is going to be the biggest element on the periodic table and who's going to be the smallest element?
Francium is the biggest.
Francium is going to be the biggest, okay? And who's going to be the smallest?
Hydrogen.
Who?
Hydrogen.
Hydrogen?
Oh, yeah.
Nope, helium. Helium is going to be the smallest. Okay, let's see. Okay. Okay, ionization energy. Ionization energy is the energy to remove one electron from a neutral atom, a neutral gaseous atom. So the energy that it takes to remove one electron from a neutral gaseous atom. Now, we know if we look on the periodic table, right? And we know that group 1 metals, they like to lose an electron. Let's see. So group 1 metals, these guys, all of these guys want to lose an electron because then it makes them that much like neon, right? So do you think it's going to take a lot of energy to remove one electron from those guys? So they want to get rid of an electron. Do you think it's going to take a lot to sit there and convince them to get rid of an electron?
No.
No. So they're going to have a very low energy level where we have fluorine here, which needs one electron to be like neon, right? To be like the noble gas neon. Do you think he's going to want to give up an electron?
No.
No, he's going to fight you for it. He wants to take your electron. He doesn't want to give anything up. He wants to take it, right? So he's going to have a very, very strong electronegativity. So if we think about it, as we go from left to right, we would expect the ionization energy to increase or decrease. Is it going to be the energy it takes to remove one electron? This guy, he's not going to want to lose anything. He's like, I'm this way. I need one electron, be like a noble gas. I need to gain that one electron. Do you think he's want to give away anything? No, he's not. He's going to be like, no, there's no way in hell. You've lost your mind. Where lithium is going to be like, oh, here, you can have it, right? Because he really doesn't want it. Okay, so ionization energy is going to be really low here, and it's going to be really, really high here. Okay, are you with me? Okay, so as we go from top to bottom, ionization energy is going to be lower at the top compared to the bottom. Francium is going to be like, you know, it's going to be like dropping electrons next to itself. Oh, no, it's not mine. That's yours. Go ahead, take it. You know, so it's going to be really easy to take an electron from francium, where we know that fluorine is going to be almost impossible. And we know that the noble gases, they're already noble. They're not going to want to give up anything. So there's going to be the highest compared to everything else, right? Okay, so it is 2:30. It is time to go. We have to call it a day. We'll finish this up on Wednesday. But fortunate for us, we went over parts of chapters 12, parts of chapters 13. So we're doing pretty good.
Dr. Henry,
Yeah.
they're leaving and they're sending off, and they weren't really paying attention.
At all? Perfect. So then I'll put it on the test. For Avenel.
Hey, Doug, can you give me my backpack, bro?
Okay, so I'll see you guys on or tomorrow.